Okay, it works. So, hello everyone. I will talk about my PhD research, which was electron transport in proteins. Until the 2000s, proteins were considered insulators, but new experiments showed pretty interesting behavior. Mind. Yeah. There are two different ways you can measure the conductance of a protein. One is the single protein measurement. They do it mostly in Arizona. You have a nanopore, you place your protein in it, and you measure the conductance with an STM tip. The other one is sort of like a sandwich. You have two electrodes and a protein layer between them, and you apply some voltage and measure the current. In these measurements, they also change the temperature. So the behaviors that I was talking about are the followings. When they measured the conductance of these single proteins, they've got nanosiemens. And when they increased the size of the protein in these nanopore, like they use different proteins, meaning that the distance between the electrodes were increased, the conductance did not decay exponentially. So we can say that it is not tunneling. That is the mechanism behind protein conductance. In these type of measurements, when they changed the temperature, they saw that the conductance is still there. It is still measurable even at 4 kelvins. So it is not something purely thermal either. And also, in these type of measurements, when they had a streptavidin protein and they just placed the protein inside this nanopore and measured the conductance without any direction or any fixed position, they've got distribution. But this distribution changed when they had a biotin on the STM tip that binded to the protein. So that means that coupling to the electrodes plays a very important role. And also, we think that there are high conducting and low conducting parts of proteins. When you want to describe the conductance of proteins, you could think about the Landauer formula, but this is not applicable at high temperatures. So you can turn your head and find yourself a Marcus theory, but it is for electron transfer and for high temperature. And electron transfer and electron transport are not the same. So the main difference is that in electron transfer, you can have ions, you can have a solution, and also there is a donor and an acceptor site in your protein. However, in electron transport, you don't have a solution, only the structural waters when they carry out these measurements. And also you do not have a donor and an acceptor site. The electrodes are kind of a donor and an acceptor. So you can use also a quantum master equation if you consider the whole problem as an open quantum system. And what we did, and I won't go into very deep details, what we did is that we combined a Liouville quantum master equation with the Landauer formula. With this Liouville quantum master equation, we have this descriptor that describes the interaction between our system and the phonon bath. And the pretty cool thing about this phenomenological descriptor is that it drives the system to the correct Fermi-Dirac distribution if there is no external perturbation. These are just the parts of it. Yes, and as I said, we used a Landauer formula that was already used for the conductance of molecules. And The most important thing that we should concentrate on is this evolution operator of the density matrix. If we plug it into our formulas, we will get a very simple one at the end. I said I won't go into deep details, which is this. And if we assume that the relaxation to equilibrium is much, much faster than the escape of electrons from the system, then we can do an approximation. And also, we can do an approximation and eigendecomposition of this evolution operator, because calculating its inverse, it's very complicated. It's a very huge matrix for a protein. So at the end, we will get a formula for the conductance, and we have three terms. First, describes the Landauer-Büttiker type of conductance. It is temperature independent and decays with the distance between the electrodes exponentially. We have a thermal excitation-based term that describes the, I think this is self-explanatory, but so this describes the process when an electron from the electrode enters the protein via thermal process, and then it will just leave the protein at the other electrode. These are the left and right electrodes. And we have a new term too, which describes a mixed process. And in this process, the electron tunnels from the electrode, from one of the electrode, to the protein, and then the protein leaves the, and the electron leaves the protein via thermal process. So this is a mixed process, and we need it to in a symmetric form. So this describes the same, just the electron enters at the left electrode and leaves at the right. But I think we all love visualization, right? We all want to see something. So one of our goals was to show these conducting parts of proteins. And for that, we used these functions. And this describes how easily an electron can enter the protein thermally. And this describes how easily the electron can enter the protein with tunneling. So when these two have high values at some point of the protein structure, we can be sure that the conductance measured on these points will be high. So we can visualize that. And for that, we had good candidates, because you may know that there are some bacteria, here Geobacter sulfuredescens, who create or have these nanowire type proteins. They have heme inside the protein chain, and they can be very, very long, and they use it to export electrons to the environment, and also for interspecies electron exchange. So experimentally, it was shown that mainly this heme part is conducting, but we wanted to show it theoretically. So we took these nanowires that Geobacter sulfuredescens produces, and we just showed these functions. So you can see that indeed these high values, these high value regions, are where the hemes are in the proteins. And also they are very similar for the tunneling part, and also for the thermal part. So we can say that electron transport is mainly on this part of the protein. But what we could also do is simulate this conductance. And for that, we wanted to see the distance dependence and also the temperature dependence of this conductance. Here you can see the whole conductance and also the terms separately. So about the distance dependence, you can see that there is no exponential decay. But also you can see that if you look at the Landauer-Büttiker term, as expected, it decays exponentially. And this exponent is very similar to what was measured in another protein that contained these heme molecules in a chain. And also you can see that the conductance at very low temperatures is not zero either. So we can reproduce what was measured for proteins generally, because not all these proteins were measured in experimental setups and not in those way that I was talking about at the very beginning. And we could also reproduce another experimental observation, namely that OMCZ and OMCS nanowires have different conductance levels. OMCZ is more conductive than OMCS, and we could reproduce this when I simulated the conductance and when I calculated the conductance of these protein molecules. So I just want to give you a picture about how the workflow was during these processes. So I always downloaded a 3D structure from the protein data bank, and from that I could plug it into a quantum chemistry program. I've got back the Hamiltonian and the overlap matrix, and from that you can calculate pretty much anything, but mainly the wave functions and the spectrum. And after that, you can calculate the conductance with the formula that we have, but you can also do this visualization if you go to the other side of this picture. So just to conclude, we created a model where we have 3D visualization, but also we can simulate the distance and temperature dependence. And this is computationally feasible because we use this semi-empirical extended method and also the assumption that the relaxation is much faster than the escape of electrons from the system. But we don't know a lot about what is happening inside the protein and why proteins are these good conductors. I will just give the microphone to Gabor and he will talk about it.
Okay, so as you could see, both on the experimental figures and on the calculated conductances between various points, there was a very wide distribution of conductance depending on the sites. And this is a well-known thing in solid-state physics when you have a system which is in a critical state, and we could connect this detailed calculation to our previous work on quantum criticality in proteins. Oops. No. Can we step here? Oops, this way. No, that goes forward only. Sorry. Okay, so here comes this problem, which was first faced by Albert Szent-Györgyi, who already was mentioned here, that he had a theory that proteins should have a collective kind of level structure. At his time, he was thinking about periodic systems, which are good conductors, and he was thinking about semiconductors, and a lots of effort was put into proving this, but all these efforts failed at that time in the 60s, 70s, and 80s, and nobody could come out with a good model for the energy levels of the proteins. And in solid state physics, there were developments in the 90s when they showed that if you have a disordered lattice, until the disorder in the conducting lattice is small, you get very good conductance in accordance with the Landauer formula or any formula you would like. And if you have a very dirty system, then everything gets localized. And in between these two extreme states, there is a single point, a critical state, where the system is neither a perfect conductor nor an insulator, but it is in a so-called critical quantum state where the wave functions are fractals. The difference between a localized state is that the localized state has one peak. So when an electron enters into this peak, then it stays there. Here, if you have a conducting system, you put in an electron and it can travel through the system. In this situation, if you hit a point where the wave function has a high point, then the electron can appear far away in another peak point. And if you measure the conductance between these two points, then you measure high conductance. If you measure between this point and this point, then you measure basically zero conductance. So this is a characteristic feature of this critically disordered systems. And if we go forward, there are very nice properties of these critical states. So if you have a solid state system which is critically disordered, so it sits in the critical point of the so-called Anderson transition between localization and delocalization, then you get sort of mixed properties, like the wave function is multifractal, the wave function densities are correlated in a power law fashion, and not exponentially like in the localized state. And in solid state physics, to get a sample which is critically doped, so to say, you have to work on it. So practically, you should put various number of disorder on the sides, and then you select the ones which are roughly the critical ones. So it needs extreme tuning in solid state physics to get to this funny critical state. And it's not typical in nature that you find such solid state systems. And there is another property. When you look at the energy levels of a system which is in the critical quantum state, it's the spacing distribution of the energy levels is strikingly different from both the localized and from the conducting sites. For weakly disordered systems where the system is conducting, you get the so-called random matrix theory distribution. So you can model the system with a random Gaussian matrix, and then basically the wave functions are Gaussian distributed, and in average they are the same on all sides. If you are in the localized regime, then you get totally localized states, and energies are just random numbers, so they follow the Poisson distribution. So the spacing between the levels is Poisson distributed or simply exponentially distributed. And there is this single critical point where you get a different distribution. You can model this distribution with the semi-Poissonian distribution. Semi-Poissonian means that between each random two random points, you put a point in the middle and measure the distances. That's why it's a semi-Poissonian distribution. And we tested this theory on proteins at the beginning of the decade, and it was very interesting that in addition to these properties, there is another very interesting feature of this critical state is that if you measure how quickly quantum coherence decays in a localized system, it decays well. It is good, but it's localized to one side. If you have an extended wave function, then due to the many noise sites, you lose coherence very quickly. But if you are in the critical point, then it turns out that coherence dies out only algebraically. So it has a power law decay. So it's much slower than in any normal quantum system. And we thought at that time that this might be advantageous for quantum biology, because if a molecule would be in a critical quantum state, then it could save coherence for a very long time, for an anomalously long time, and it would have very interesting conducting properties like the ones which we have seen both in the simulations and in the experiments. Okay, so the theory was that if we have a biological system in this critical state, it is very advantageous because it's robust, but it can conduct very well. But quantum coherence stays alive for a very long time, and these molecules can then do very interesting things both in the conductance domain, but also in other respects. And we carried out our early calculations, and this is what I will show, but we repeated them since then with tight binding DFT calculations, and the same results. We could repeat these results with more advanced methodologies. What we could see early on was that if we just plot the wave functions like the HOMO, LUMO wave functions of proteins, this is just plot. These are just the probabilities, so squared wave functions of a large protein. This was myosin, and you just study this as a fractal. You can measure its fractal dimension, and you get out a dimension of 1/2 if you look at it in this this representation. So we could see immediately that the proteins which we could study really have fractal wave functions. So this was very promising. But also, if you look the level statistics of these proteins, they absolutely reproduce the theoretical curves of quantum criticality without any tuning. So in solid state physics, you have to put an effort to get such energy level distribution, and in proteins, this is done. They are sort of designed that way. They are naturally sit in the critical point of the localization, delocalization transition, and even the deviations from the semi-Poisson distribution, which is just an approximation, is exactly the same as in mathematical systems like the rhomboid billiard, where they invented first this distribution. So the proteins somehow naturally tune themselves to this critical point. But it's not just proteins, but all small molecules which have a part in electron transport or transfer in biological, metabolical systems. You could see this. So all of them will follow this critical, the energy level spacing distribution will follow this law, which is in the critical point. If you look at biological molecules which don't play a role at all in the biochemical processes in electron transport, like your skin or hair or whatever, then they are insulators, and they show the Poissonian statistics. And there are few molecules, steroids, which show the random matrix distribution actually, but most of the molecules are in either categories. I skip this because you have seen this already. And then we recently studied this more closely, not just the level spacing distribution, because in the meantime, new characteristics were invented, like the ratio of two nearby level spacings has also a theory now, and we could repeat this, and we could see that it's neither the Poisson nor the Wigner or random matrix distribution, but all proteins which were mentioned here, they all sit near to the critical point of this localization, delocalization transition. But we could do more. We could study how quickly the wave function spreads, and in these critical systems, it is spreading according to a power law, which we could calculate, and it has a critical exponent, which we could then get out of these calculations, and we could measure now the real space dimension of this fractal, which turned out to be a two-dimensional fractal in 3 dimensions. And we could reproduce also the other critical exponents. So this is the wave function density correlation, which follows a power law for all these proteins, and they are, without any tuning, fall on the same line. Also, if you study how the wave function spread over the protein, they all follow this theoretical power law behavior. And then We could even reproduce the dimension, the fractal dimension of these wave functions in the energy domain, and corresponding to two dimension in space. Here we find the theoretical 2/3. 3 is the 3 dimensions. 2 comes from the 2 which I showed you before. And all in all, we have a more precise view of proteins, and practically all proteins what we studied, which showed up in quantum conductance experiments, all show this mysterious criticality. So it seems that evolution selected these proteins, and this is why electronic processes in proteins in your body, in any biochemical processes, electron processes are much faster than you would imagine based on a localized system. And we should change how we calculate conductance and other properties, electronic properties of proteins, because they are not short-range correlated, but long-range correlated objects in physics. Thank you.